Telescopes, a Genius Hour project by Molly O'Driscoll. #WeltyPhysics. What is a telescope? Well, you've probably seen one that looks a lot like one of these three. It is an optical instrument designed to make distant objects appear nearer, containing a region of lenses or of curved mirrors and lenses, by which rays of light are collected and focused, creating a magnified image. In 1608, Hans Lippershey Holland, an eyeglass maker, asked for a patent on a certain instrument for seeing far. He was denied the patent for a telescope because others at the time had similar instruments, and the design was far too broad that anybody could claim they were the inventor. In 1609, Italian physicist and astronomer Galileo became the first person to point a telescope skyward. Although the telescope produced images that were very fuzzy due to the quality of the glass, Galileo was able to make out sunspots on the sun. He was the first person to discover this, as well as make out mountains and craters on the moon, and see a ribbon of diffuse light arching across the sky, which would later be identified as our Milky Way, not the candy bar. Galileo was inspired by a certain device used for ages. The device was called a spyglass, and it was used to magnify distant objects on Earth. As soon as Galileo learned about the device, he built one and set about improving it, creating the first refracting telescope. A refracting telescope has two lenses. The convex lens is the primary or objective lens where the light rays enter. The second lens is concave and is the eyepiece, where you look to see the magnified image. Over time, they have certainly improved from Galileo's design to the modern-day telescope. So here again are the two lenses used in telescopes, convex and concave. But in this diagram I'm about to show you, I'm going to use two convex mirrors to show a refracting diagram. So here's the ray diagram. First, I'm going to draw the principal axis line, and then the two convex lenses. And each lens has two focus points. So, for example, let's say our image is a tree. So there are three rules for ray diagrams for lenses. An incident ray parallel to the principal axis will refract through the focus. And then an incident ray through the focus will refract parallel to the principal axis, and an incident ray through the center of the lens will go straight through the lens. And with concave lenses, if the image is outside the focus point, then the image will always be real. If it is inside the focus, like the second convex mirror, then the image will be virtual, and when we look through the lens, our eyes will revert the image. Here is the ray diagram drawn out more cleanly on paper. And to be more clear, a real image comes from where the light rays are focused, and a virtual where the light rays appear to come from but don't. In England 1668, Sir Isaac Newton created the first refracting telescope. He created the first reflecting telescope because he found too many problems with the refracting telescope because it had chromatic aberration. What is chromatic aberration? It is the fringes of color that surround bright objects seen through a glass plane. As light passes through a lens, it breaks up into various colors because the glass bends the colors by different amounts. Newton's solution was simple. He took the lens out of the telescope and put in mirrors, which helped bring the light to a focus. But how does it work? Light from the object being viewed is collected by the concave primary mirror and reflected into a smaller secondary mirror, sometimes called the flat. The flat is inclined at 45 degrees to the axis of the telescope and reflects light to an eye lens, which forms an image. Here again is a picture of Newton's telescope. You can see that it was very small at first and has a sliding design so that you can focus the mirrors. And then here is a modern interpretation. Now, what are these lights or light rays that help us see the magnified images in a telescope? Light is the smallest amount of energy that can be transported. It is a photon. It is electromagnetic radiation within a certain portion of the electromagnetic spectrum. The word usually refers to visible light, which is visible to the human eye and is responsible for the sense of sight. Of course, there are others on the electromagnetic spectrum, but none that we can see. A common reflector telescope is the Schmidt-Cassegrain, invented in 1942 by James Gilbert Baker. It is a combination of the Cassegrain reflector and a Schmidt corrector plate. In the Cassegrain reflector, parallel rays of light entering the telescope are reflected from a large concave mirror toward the focal point of that mirror, which is called the prime focus of the telescope. Before reaching the prime focus, the light rays are reflected again by a small convex mirror that bring them to a focus near a small hole in the center of the main mirror. The Schmidt corrector plate is an aspheric lens which is designed to correct the spherical aberration and the spherical primary mirror it is combined with. Together, this design reduces blurring of the image caused by the sphericality of the lens or mirrors. The Hubble telescope was launched on April 24, 1990, on the Space Shuttle Discovery from Kennedy Space Center in Florida. Hubble, the observatory, is the first major optical telescope to be placed in space. It has an unobstructed view of the universe. Scientists have used the Hubble to observe the most distant stars and galaxies, as well as the planets in our solar system. The Hubble does not travel to stars, planets, or galaxies. It takes pictures of them as it whirls around Earth at about 17,000 miles per hour. It is a basic reflector with a 94.5-inch mirror. It is packed with instruments that will give astronomers clear views of the universe in visible, infrared, and ultraviolet light. Is it a time machine? Yes and no. Because light takes time to travel long distances, the range of the Hubble makes it function similar to a time machine. The light it views from the remote objects only reveals how the object appeared when the light left it, not how it appears today. In addition to gazing at the early universe, Hubble also helped astronomers see how much time had passed since the Big Bang by measuring a special kind of pulse star known as Cepheid variable. They were able to narrow down the age of the universe from its prehistory range of 10 to 20 billion years to a more precise 13.7 billion years. Soon the Hubble's time will come to an end, and within the next couple of years, the James Webb Telescope will be its successor, and will have the exact same purpose as the Hubble. The end, and thank you for watching.